morning. I always want to think about how I develop an origin story for this paper. And it goes back 26 years, I think, when I was working on blending together non-probability sample with probability sample in terms of RDD and looking at propensity score adjustment to try to be able to blend those samples together. And then move forward to about 2012, 2014. Mansour Fahimi and Francis Barlas and I were working on developing or improving the calibration technique to try to blend opt-in sample together with probability, the knowledge panel. And working with Mansour, he always indicated that his dissertation was based on studying how you blend samples together in probability-based samples. And he said, well, you always use effective sample size to blend them together. And I said, well, with the opt-in sample, if they're more biased, they have more numbers than the probability-based sample, and they're more efficient because they've used quotas. Aren't you going to introduce more bias into the blended sample? And his response was, well, effective sample size works pretty well. So this paper sort of emanated out of the little debates we've had over the past 10 to 12 years. And it also comes out of a debate last year, or I was sitting in on a Zoom call or a Teams meeting with a CDC group, not the one that we're going to talk about today, but they're doing a CDC Omni study, and so they're out of the Atlanta office, and they were comparing, or they were using both Amerispeak and Knowledge Panel and blending them together. And for this particular study, it was looking at screening for specific cases that had children in the household. So it was a very subgroup, and they said they're just going to blend the samples together using the weights that were created, the demographic weights. And then I stopped the meeting. I said, well, wait, aren't you going to use the relative or the effective sample size of the two different samples to blend them together? So eventually we did, and we had debates about whether you trim the weights first or don't trim the weights. And I said, I think you would want to not trim the weights to have the most accurate estimates. So there are debates out there in the world about how you blend samples, what types of weights you use when you blend samples. And then I was also the chief methodologist for the rounds 1 through 5 with the NCHS studies for Ipsos to looking at this knowledge panel. We were running parallel with Amerispeak, and the rounds 1 through 5 data were released on public release. So I decided to use those data, actually the rounds 1 and 2, because there are a lot of benchmarks in there, 2 probability-based samples, and I could look at how we could blend those samples together. So if we can continue. And I'd like to thank my co-authors, Megan Hendrick and Jared Cooper-Smith and Lisa Chan, for all different components of helping on this paper as well. This does it. Okay, good. And I just want to make sure that you know that NCHS doesn't necessarily authorize or guarantee the backing of what we find here. And I will disguise Amerispeak and Knowledge Panel to the extent to which it's disguised in the papers and presentations that are publicly available. You see these 2 sources where you can get the data, the documentation, everything about the studies. It's the rapid survey systems. They're interested in trying to do faster turnovers of surveys that would help supplement the NHIS and a variety of other surveys that take longer times to get in field. It uses both Amerispeak and Knowledge Panel. So with 2 separate probability-based samples being fielded with the same questionnaire, and each one having lots of benchmarks, it became a prime example of how we could actually start doing some comparisons of survey estimates by 2 different probability-based samples and how we might be able to blend them. Looking at how you identify biases, 2 major approaches have been used that you'll see. Individual item approaches, where you look at sort of the standard error and whether the estimates by item are within the population estimates, using typically federal surveys or some large gold standard surveys as well. So specific items, and you will see these comparisons, and you've seen a couple actually already of specific items being used. And then there's the examination of total divergence across a number of different benchmarks. And this is what we're going to focus in on, is across a number of different benchmarks, because I believe, and I think we can improve, that sample error, the margin of sampling error, reduces down to almost zero when you have between 6 to 8 different benchmarks, because remember that sampling error is a random influence on estimates. And as you increase your number of estimates, the randomness essentially gets washed out. And you're looking at basically bias as you're using more and more estimates to form the average value. And you can look at average deviations in terms of absolute deviations and sort of sum them and average them, which we're going to do in this paper. Or you can look at root mean square error, which John Krosnick likes to. And I promised him I will do this as well next week. So if you want to send for the paper, we'll include the root mean square in it. And it may even have bootstrapping error estimates too. So as well as for the absolute differences. So as you see here, you can treat each sample as equally valid. Remember that call I was on where they said they're essentially going to pool the data, pool the weights that they got, and treat them as one unitary sample. They're coming from two different probability-based samples. So that's what I call pooling weight. And then you can combine the weights based upon their relative effective sample sizes, which involves both the number of cases plus the weighting efficiency. So it's multiplied by the weighting efficiency to give you the total effective sample size. And then you essentially will adjust the weights to be based on the effective sample size. And then you typically multiply up to rescale to the total number of the sample. So it's a fairly simple procedure. That's another way of typically blending these samples together. So we'll present both approaches as well with this. You'll see here, I'll do some summaries of rounds 1 and 2. Is that the elapsed time or the time to go? Geez. Rounds 1 and 2, you'll see invited sample, completed sample, effective sample size, weighting efficiency by both NOEC and Ipsos, and you'll see the source that I get it from underneath there. And then they present provider 1 and provider 2 underneath on these other documents as well. So you'll see the cumulative response rates and the total survey duration, and also field periods. In the round 1, round 2, still pretty large sample sizes, right? And you see a difference in terms of weighting efficiency between the two different samples. And then that affects, and also a smaller sample size in the NORC sample. So that affects how they get blended together. And the topics of these two somewhat differed, the two different rounds, but they shared a number of topics in common. So we had 7 secondary demographics in both, and we had 22 health-related in the first and 13 health-related in the second. And you see some of the examples of these items too, in terms of the health-related benchmarks that I use the 2023 NHIS essential data that was the final 2023 data. These studies were running in 2023, so we have a benchmark and we can compare them accurately with the benchmarks as well. And you see the secondary demographics that were common to both as well. And then we use the sample weights that were constructed by each organization. And they were similarly derived, but they had some differences, just to note. So you can read about that in their reports. But in general, they had similar common demographics used as targets. And as you see here, we have one provider being less efficient with fewer cases and one provider being more efficient with more cases. And so again, computation of survey estimates, we did that for each of the items, and we calculate a pool of unweighted and weighted estimates. So I always, like last year, I reported on the differences between no weighting and found that weighting helps probability samples, but weighting is very inconsistently related to improving accuracy in non-probability samples. So I compare these two as well. And as you see and squint, you can get the copy of this if you want, but the NHI weighted, I look at NHIS unweighted in terms of the values they got, and then the provider one, provider two, pooled value, and then the weighted values of provider one, provider two, the pooled weight, and then the effective sample size weight, the values that you get in terms of the measures. And this is for round two, and this is the average. So there are just two main graphs here. These are the average biases unweighted across provider one, provider two, pooled, and effective sample size. And you'll see that weighting helps. Weighting helps in terms of all the provider one and provider two. The provider one, though, appears to be more biased than provider two. And that's also follows through with the results for round two. That provider one is more biased over to the right when you're looking at the weighted values. It's more biased by about 50% more bias in provider one than it is provider two. That affects how you pool the data. So when you pool in the two values, they tend to be an intermediate amount of bias, which means, but because provider one was lower efficiency and lower sample size, it doesn't affect the pooled values as much. So the discussion, as you see, the provider one in both rounds appeared to be had more average bias overall across all measures than provider two. And then with both pooled and the effective sample size weights, blending the samples did not lead to a reduction in bias below that which you find with provider two. So that means that you're blending in additional bias when you're blending samples together, even with probability-based samples. So Mansour should know that probability samples are not equivalent. That's the assumption is that they're equivalently biased, but they do not, and they don't counterbalance their biases. The issue, though, is that we often encounter these difficulties, often blending in opt-in samples. And we should realize that probability sample is not a guarantee of quality. There are differences in bias. Oftentimes it may be due to how the sample is recruited or how they're maintained, retained. So blending samples, we always have to realize that number of participants and bias are probably the more important factors and not effective sample size. I guess that's what you should come away with. I dropped the mic.